In this class, let us discuss the radiative transitions in hydrogen atom. That means the electronic transitions between different energy states which result in emissions or absorptions of radiations. That means which result in the formation of spectral lines. Now let us start with the result in an idea in classical electrodynamics. Electric dipole radiations. Electric dipole radiations. So the result in classical electrodynamics is that the most efficient radiating system, the most efficient system of radiating electromagnetic radiations is an oscillating dipole. Okay, you consider a dipole like this. Suppose these are two electric charges. Let us say this is minus q and this is plus q, separated by a distance, let us say d. Then the dipole moment p is charge into distance. Okay, and the direction of the dipole moment is from minus charge to plus charge. Magnitude is charge into distance between the two electric charges. So when this dipole is oscillating by swapping the position of the charges, position of positive and negative charges, an electromagnetic radiation is emitted, and the power of this electromagnetic radiation, okay, the power of the electromagnetic radiation is given by p square omega square divided by 12 epsilon 0 c cube, where this p is the magnitude of the amplitude of the dipole moment, amplitude of the oscillating dipole moment, and omega is the angular frequency of oscillation of this dipole. Okay, so this we have obtained from classical electrodynamics. Now when you consider hydrogen atom, for the hydrogen atom to be an efficient radiating system, it also should have an oscillating electric dipole moment. Okay, but in the case of hydrogen atom, the electric charges and the positive and negative charge in the hydrogen atom, that is, nucleus has the positive charge, it is compact, it is localized, the positive charge of the nucleus is localized, but the negative charge of the electron is not localized. Okay, we know that depending upon the different quantum state of the electron, its charge distribution varies with the radial distance, it varies with the angular variables. Okay, so there are different distributions of charges in hydrogen atom depending upon the quantum state of the electron. Then how do you define the dipole moment, electric dipole moment of a charge distribution? Okay, so suppose we have a charge distribution like this. Okay, then let us consider an origin, a coordinate system. This is the origin. Okay, then we divide this charge distribution into different small, let us say, small volume elements. Okay, each with the volume some dV, volume dV. Okay, now suppose one such volume element is from the origin at a distance, at a vector distance r. Okay, now in this volume dV, it has a charge, let us say dq at the position vector r. Now this dq of this volume element we can write as charge density at this volume element into the volume element dV. Okay, charge density means charge per unit volume. Okay, into the volume element dV. Then that charge per unit volume into volume of this small element dV will give you the charge in this section. Okay, now the dipole moment, let us say dP, the dipole moment of this small section. Okay, it is defined as the charge dq at, of this small section into the position vector r. Okay, so the dipole moment of a small charge distribution or an infinitesimal charge we can write as charge into the vector. Okay, vector from the origin r. Here we have used the same idea here. Dipole moment of a of a single dipole, okay, with charges plus q and minus q separated by a distance is charge into here we have considered one of them as the origin, and the charge from the magnitude of the charge into distance from the other charge. Here the other charge is taken as the origin, so q into distance. The same idea we have used here, okay, even though this is a distribution of continuous distribution of charge, we have separated, we have divided into small volume elements. So each volume element we can consider as an approximate point charge, so having charge dqr. Then the dipole moment with respect to some origin here is the position vector from the origin into charge, okay, so or charge into position vector from the origin. Okay, so from here we can say what is the dipole moment due to the entire charge distribution. Okay, the dipole moment due to the entire charge distribution is obtained by integrating this. So it is integral r dq, integrated over all space. Okay, now what is this dqr? Okay, if you substitute for dq dq at r, what is that? It is charge density at the point r, at the position vector r, into volume element d. So this is the dipole moment due to a continuous charge distribution. Integral over all space, okay, integral over all space, position vector r, charge density into volume element. We are integrating, it's a volume integral of position vector into charge density. Okay, this is how we define dipole moment of a continuous charge distribution. So for hydrogen atom also, this is the way to define the dipole moment of the electron. Okay, okay, or dipole moment of the hydrogen atom. Now what is this rho for in the case of hydrogen atom? Okay, the charge density rho of r, charge density at r, is, we can write as the electric charge of the electron. We are talking about the charge density of the electron cloud, right? So this is electric charge into electric charge of the electron cloud, which is minus E, into probability density. Probability density of finding the electron at the position vector r, at the radial distance r from the origin. Here the origin is the position of the nucleus. Okay, so charge density is electric charge density is equal to electric charge of the electron cloud into probability density. So we can write this as minus E into, what is the probability density? It is psi star psi, where we have to take the total wave function, okay, the time dependent part also, because it is the time dependent or oscillating nature of the dipole moment that produces electromagnetic radiation. Okay, so we have to consider the total wave function, not simply the solution of the time independent Schrodinger equation, which has only spatial dependence. We have to take into account the time dependent part also. So electric charge minus E into psi star psi, that is the probability density of finding the electron at a position vector r from the origin. Okay, so then how do you let us use this definition of the dipole moment. Then the dipole moment of hydrogen atom we can write as dipole moment is minus E integration over all space. Okay, we are using this definition. So it is integration over all space, position vector r, charge density, volume element, right? So charge density is this. So we have a position vector r. For charge density I am substituting minus E psi star psi. Minus E is taken outside. Psi star psi volume element. Okay. Now look at this integral. Okay, this integral is exactly the expectation value of the position vector r. Okay, so the dipole moment of hydrogen atom can be defined as minus E into the expectation value of the position vector r. So what is the condition for radiative transition in hydrogen atom? the electronic transitions that emit electromagnetic radiation. The condition is that since this is the dipole moment of the hydrogen atom, electric dipole moment of the hydrogen atom, the condition is that this electric dipole moment should oscillate with respect to time. In other words, this expectation value of position vector r, okay, this should be oscillatory. It should be time dependent and it should oscillate in time with some frequency. Okay, for an oscillating dipole, the power radiated is given by this. Okay, it is proportional to the amplitude of dipole moment and angular frequency. So the idea is that the electric dipole moment of the system, or electric dipole moment of the system should be oscillatory. It should oscillate with respect to time. Since electric dipole moment of hydrogen atom is given like this, this quantity should be oscillating with respect to time. In other words, since minus E is a constant, this expectation value of position vector should be oscillatory with respect to time. Let us briefly recall the idea of stationary states in hydrogen atom or in any atom. Suppose the electron in the hydrogen atom is in a particular quantum state of energy En. Okay, so electron is in the quantum state with principal quantum number n. Suppose its energy is En. Okay, then what is the wave function of the electron? Let us say the total wave function of the electron. Let us label it as psi n. It depends on position vector and time. Okay. So this we can write as a position dependent part phi n r into a time dependent part. See, what is the idea here? In a hydrogen atom or in any system where the potential energy is independent of time, the total wave function, the solution of time dependent Schrodinger equation, we can write as product of two parts, a space dependent part and a time dependent part. If we substitute this product in time dependent Schrodinger equation, we can do separation of variables. Okay, and the time dependent part we can exclusively obtained as e raised to minus I e t by h cross. Since this particular quantum state has energy En, it is e raised to minus I e n t by h cross. So this is the space position dependent part. Okay, and this is the time dependent part. So this is time dependent part of the wave function, of the total wave function. Now in any system with time independent potential energy, in hydrogen atom potential energy is time independent, minus e square by 4 pi epsilon 0 r. This is so in the case of particle in a box, in the case of harmonic oscillator. So in any system where potential energy is time independent, we can always separate total wave function as a position dependent part and a time dependent part, and the time dependent part will be exactly like this, e raised to minus I e t by h cross, where E is the total energy of the system. What about let us come back to the case of hydrogen atom. What about this position dependent part? This will be the solution of time independent Schrodinger equation. Okay, solution of three-dimensional, in the case of hydrogen atom it's a three-dimensional Schrodinger equation. Okay, three-dimensional time independent Schrodinger equation. Okay, it is this space dependent part we have written as actually this phi n r. Okay, this we have written as a radial part which depends only on the radial variable, and a polar part or angular part which depends on polar angle theta, and an azimuthal part, okay, which depends only on the angle phi. Okay, so this space dependent part we have separated like this. So we notice that in the total wave function in this total space dependent wave function, I have written vector r. Okay, it contains it's a vector, that means it's a position vector. It has three components. If you use Cartesian coordinates, we can write these three components as x, y, z. If you are using polar coordinates, these components can be expressed in terms of r, theta, phi. So this small r, theta, radial variable r, theta, and angular variables theta and phi are the components of this position vector. Okay. So this is the idea. So total wave function we can write like this if it is in a particular quantum state of energy En. Now let us look at the probability density of the state. Okay, so the probability density of this of the electron in this, or probability density of the hydrogen atom, you can say, when the electron is in a particular energy state is psi n star psi n, right? Now if you substitute for psi n star psi n, this is phi n star r. What is psi n? We have written it as phi n into e raised to minus I e n t by h cross. So this energy, so both part we have to take the complex conjugate. So this exponential part will become e raised to plus, okay, e raised to plus I e n t by h cross when you take the complex conjugate, and psi n is again phi n r e raised to minus I e n t by h cross. So this e raised to plus I e n t by h cross and e raised to minus I e n t by h cross will cancel. So what remains is phi n star phi n. Okay, so probability density, we can see that probability density is time independent. This is time independent. It does not vary with time. Probability density of hydrogen atom does not vary with time. So this is one result, and secondly, let us calculate the expectation value of the position vector of the electron when the electron is in this particular state. So this is integration over all space R. Since position vector is a it's a multiplicative operator, we can write we can place it anywhere when you calculate the expectation value. We don't have to place it in between psi star and psi. Okay, so it is psi n star psi n dv. It's a volume element, volume integral. Now again, if you substitute for psi n star and psi n, the exponential factors will cancel, and what is remaining is integral phi n star r phi n r d. Okay, you can see that this part we have already seen. This position vector, when you substitute for psi n star and psi n, we get phi n star phi n, right? Exponential factors will cancel. So we can see this result, this expectation value of r, position vector of the electron. This is again time independent. Okay. Now earlier we have got this result that the dipole moment of the hydrogen atom we can write as minus e into expectation value of position vector, okay, or this integral, right? Now if this integral, when the electron is in a particular quantum state, this integral is time independent now, okay, it's time independent. That means the dipole moment of the hydrogen atom is time independent, it is not oscillatory. So if the electric dipole moment of the hydrogen atom is not oscillating, then it will not radiate any energy. The hydrogen atom will not radiate any energy. So quantum theory predicts that when the electron is in a particular quantum state, then the hydrogen atom will not radiate any energy. So therefore, this state, when the electron is in a particular state of energy En, for a particular quantum state of a fixed energy, then such a state is called a steady state or stationary state. Okay, that's why this state is called a stationary state. What is stationary here is the dipole moment is stationary, and also probability density is stationary. Probability density is time. Here stationary means time independent. Okay, so the probability density does not change with time. The average position of the electron does not change with time. Okay, if you calculate the average value of any physical quantity, expectation value of any physical quantity, any operator, you will see that does not change with time. Okay, so since this expectation value of position vector, expectation value of other operators, probability density, all these factors does not change with time, such a state is called a stationary state. So this is the idea of stationary states or steady state. So remember that this was a postulate in Bohr atom model. One of the postulates in Bohr atom model is that when the electron is in a particular orbit around the nucleus, then it will not radiate energy. These orbits are non-radiating paths or stationary orbits. Okay, so even though it was a postulate in Bohr model, in quantum model of hydrogen atom, this is a result that we can deduce from fundamental ideas. Okay, we have seen that when the electron is in a particular quantum state, probability density is independent of time, and expectation value of position vector of the electron is independent of time. When expectation value of position vector of the electron is independent of time, the dipole moment of the hydrogen atom is independent of time. When there is no oscillating dipole, there is no radiation. Okay. Then the question is, when does the electron undergo, or when does the hydrogen atom emit a radiation? Now, suppose the electron in the hydrogen atom is in an excited state. Suppose it is here, n equal to 3 state, or n equal to 2 state. Suppose it is in a state above the ground state, which is, let us say, n equal to 1. Then it undergoes de-excitation. It can remain in this excited state only for a short interval of time. We know that it's of the order of 10 raised to minus 8 seconds. Then it undergoes quantum jumps downward. Okay, it will go to n equal to 2 state. It can also go directly to n equal to 1 state. So when it undergoes de-excitations, when it undergoes these quantum jumps, the difference in energy between two states is emitted as a photon of radiation. This is how we get spectral lines. And this type of transitions are called spontaneous decay. Okay, when the electron is in an excited state, in a higher energy state, it spontaneously undergoes decay, and the electron undergoes jumps down, or it undergoes quantum jumps to lower energy states. It's called spontaneous decay, and the emission of spectral line by this type of decay is called spontaneous emission. What is the reason for this? Why is that? We know that each of these states are stationary states. As long as the electron remains in that state, there is no emission of radiation. So why can't the electron remain in an excited state? Or what is the cause, what is the reason for an excited state to be unstable? We say that these excited states are unstable. That is why the electron comes down to the lower energy states. But what is the reason that the excited state is unstable? The reason is that even in vacuum, there are fluctuations of electromagnetic fields, okay, which are called vacuum fluctuations. Vacuum fluctuations. This result comes from quantum field theory. So, okay, whatever we say is as a vacuum is not empty. There is fluctuating electromagnetic fields in this vacuum. So these fluctuating electromagnetic fields or vacuum fluctuations causes perturbations even in an isolated atom. If we consider an isolated atom, then because of these vacuum fluctuations, there will be perturbations in this atom. As a result of these perturbations means some disturbance. As a result of this interaction with the vacuum, the potential energy of the system will change. Okay, so because of these interaction with the vacuum, this is the reason that the excited states in an atom are unstable. Okay, and the electrons in the excited state should continuously seek lower energy states until it reaches the ground state. Okay. Now the question is, if you consider this electron here, there are two possibilities. This electron can undergo de-excitations to n equal to 2 state. Then what you get is the first line of Balmer series, right? N equal to 3 to n equal to 2. What you get is first line of Balmer series. Now there is another possibility. The electron here can directly go to n equal to 3 to n equal to 1 state. Then what you get is the emitted radiation will be the second line of Lyman series, right? Second line of Lyman series. So we can ask the question, what is the possibility for each of these transitions? Okay, what is the possibility for the electron in an n equal to 3 state goes to n equal to 2 state? What is the possibility that electron in n equal to 3 state directly goes to n equal to 1 state? So these are called radiative transitions, because when during these transitions electromagnetic radiations are emitted, we get different spectral lines. So there are different probabilities for each of these transitions. How do we calculate these probabilities? Okay, let us try to obtain when we get electric dipole oscillations in hydrogen atom, and if the electric dipole is oscillating, what is the frequency of these dipole oscillations? Okay, consider two quantum states. Consider two quantum states. Suppose the electron is initially here. Let us call it initial state I, and then it undergoes a transition to a lower quantum state. Let us say it is F, final state. So electron undergoes a transition from an initial quantum state to a final quantum state. Now when the electron is in the initial quantum state, its wave function is, let us say, psi I RT, and this is product of a position dependent part phi I R into a time dependent part. Let's say the energy of this state is EI, initial state, energy of the final state is EF. So the time dependent part is e raised to minus I EI t by h cross. When the electron is in the final state, its wave function is psi f RT, which is again a product of position dependent part and a time dependent part. This time the energy is EF, so we can see that the time dependent parts are different. Position dependent parts are also different. Okay, now so when the electron is in a particular state, these are all these states are steady states. Okay, so when the electron is in initial state I, it's a steady state or stationary state. It has a particular wave function representing that state. When the electron is in the final state, again it's a stationary state, so it has a wave function for that state. We know that when the electron is in any one of these states, either initial state or final state, there is no radiation. There is no these are stationary states, non-radiating states. Then when does we get the radiation, or when does we get the radiation? When the electron, during the transition of the electron from the initial state to final state. Then how do we write this wave function for this transitional state? Okay, how do we write the wave function for the transitional state? So during the transitional, when the electron is in a transition between initial state and final state, we can say that it is its wave function is neither psi I nor psi f, but a combination of the two. Okay, but a combination of the two. Now this combination can be different. The proportion of psi I and psi f can be different. But let us now take a simple combination of the two. This is equal to, simply let us take psi I plus psi f. Okay. So we assume that there is 50% half, it can be 50% of psi I or 50% of psi f, half of psi I and half of psi f. Now in order to make this sum, the new wave function, this transitional wave function normalized, the normalization constant, if you do this, we assume that psi I and psi f are normalized. Then in order to make this combination normalized, the normalization constant will be 1 by root 2. Okay. So we assume that this is the transitional wave function. So in general, the proportion of psi I and psi f can vary with time. Okay, but we assume that the proportion remains the same. 50% proportion is there for psi A and psi f, and this proportion remains the same over time. We assume that, but it's an approximation. So this is an approximate choice for a transitional wave function. But let us see what we can get from here. So if this is the transitional wave function, let us calculate the expectation value of R using this transitional wave function. So expectation value of position vector during when the electron is in the transitional state is integration over all space R, position vector R, psi star, this is transitional wave function, psi star psi, volume integral. Now let us substitute for this psi star and psi. Okay, then what you get is 1 by root 2 into 1 by root 2 will come from psi star and psi. 1 by 2 I can take outside. integral over all space. Okay, now this psi is 1 by root 2 psi I plus psi f, right? So psi star will be psi I star plus psi f star, and this is psi I plus psi f. Okay. Okay, now we have to substitute for psi I and psi f from here. Okay, psi I is this and psi f is this. We can substitute that here. Okay, so this is what we get when you substitute. See, from here, if you substitute for psi I and psi f, if you substitute these values here, okay, then what you get is this. I have just substituted. This is the first term is psi I star. See here. This is psi I star, psi f star, then psi I, psi f. Psi I star plus psi f star, psi I plus psi f. Now we have to multiply, then there will be 4 terms. Okay. So this is half integral over all space volume element dv vector r. Okay, then see here, when the first term phi I star e raised to I e I t by h cross, when you multiply that with the first term here, phi I star, phi I e raised to minus I e I t by h cross, then the e raised to plus I e I t by h cross and e raised to minus I e I t by h cross will cancel, and what is remaining is phi I star into phi I, right? So this I can write as mod phi I square plus, similarly when you multiply this term phi f star e raised to I e f t by h cross with phi f e raised to minus I e f t by h cross, again the exponential terms will cancel. We get phi f star phi f, or can write this mod phi f square. Then let us consider the cross terms. Okay, then the first cross term is you multiply phi I star e raised to minus I e I t by h cross with phi f e raised to minus I e f t by h cross. So one exponential term is e raised to plus I e I t, the other is minus I e f t. Energies values are different, so the exponential terms will not cancel each other. So what you get is phi I star phi f e raised to, I can take a common terms outside, so what you get is e raised to I e I minus e f, okay, e I minus e f t by h cross, right? If I take I t by h cross outside, what is remaining is e I minus e f. Okay, similarly the other cross term is multiply this phi f star e raised to plus I e f t by h cross with this one. Okay, again the exponential terms will not cancel there, so what you get is phi f star phi I e raised to, again I can take common terms outside. Suppose I take minus I outside, so minus I t by h cross outside, so what you get is e I, again e I minus e f t by h cross, exponential term. So these are our 4 terms in the expectation value of r. Okay, this is the expectation value of r. So we can see that the first 2 terms are time independent. This term is time independent. So see, what is the importance of expectation value of r? The dipole moment is minus e times expectation value of r, position vector. So if expectation value of r is time dependent, then dipole moment also is time dependent, and there is possibility of radiation, emitted radiation. But this first term here, it is independent of time, so it does not contribute to any oscillating dipole moment. Second term is also time independent, does not contribute to oscillating dipole moment. So we need to consider only the third and fourth terms. Okay, third and fourth term has time dependency, e raised to I ei minus eft by h cross. This is e raised to minus I ei minus eft by h cross. So these are time dependent part, and that e raised to I, it's like e raised to I omega t, right? ei minus ef by h cross, we can say omega, some frequency. So there is oscillatory part. So it is clear that average value of the position of the electron, position vector of the electron, has oscillatory part. So since average value of position vector of R is oscillatory, dipole moment is also oscillatory, and there is possibility of electromagnetic radiation. So what is the frequency of this electromagnetic radiation emitted? That's what we want to find out. Or what is the frequency of this dipole oscillations? Now when you look at the third term here and the fourth term here, these are complex conjugates of each other. See, phi a star phi f becomes phi f star phi a, and e raised to plus I ea minus eft by h cross here in the third term, it becomes e raised to minus I ea minus eft by h cross in the fourth term. So these are complex conjugates of each other. So let us say, if I take so let's consider let us use the fourth term as the starting term. Suppose it's some complex term, let us say something like a plus ib, then the third term is like a minus ib. What happens when you add a term a plus ib with a minus ib? Then the imaginary parts will cancel, we get 2a, twice the real part. Okay, so if we combine the third and fourth terms together, we can write the expectation value of the radial position vector of the electron as half integration over all space, okay, dv r, and this term, third and fourth term, I am not considering first and second term, the third and fourth term together, we can say 2 times real part of I am considering the fourth term. We can either consider third term or fourth term. Let's take the fourth term. So phi f star phi I e raised to minus I ei minus ef t by h cross. So let me write it here, considering only the time dependent terms, because this is not exactly equal to the total expectation value of position vector of the electron. We have removed the 2 terms. So considering only the time dependent part, time dependent terms. So what we have, let me use a suffix t here to specify that now we are interested in the time dependent part of the average value of the position vector of the electron. So okay, we get this. Okay, so we have combined third and fourth terms, then we get twice the real part of one of these terms. That's why I have chosen the fourth term. Now this 2 here and half will cancel, and this integration is over space. That means the integration is position dependent. So that time dependent part we can take outside the integral. So I can write this as the time dependent part of the position vector is real part of this exponential term I am taking out, minus I ei minus ef t by h cross, integration over all space, r phi f star phi a r volume element. Okay, so this is the expression for the expectation, the time dependent part of the expectation value of r. Now what is the time dependent part of the dipole moment? Not the total dipole moment, because what we have obtained here is not the total average value of r. So the time dependent part of the dipole moment is simply minus e times the time dependent part of the expectation value of r. Okay, so we can say the time dependent part of the dipole moment is minus e times the above expression, real part of e raised to minus I ei minus ef t by h cross, and this integral over all space r phi f, right? Phi f star r phi a r t. Okay. So it's clear that the dipole moment of the hydrogen atom is now oscillating, and this is the oscillating part. Okay. And what is the frequency of oscillation? This ei minus ef by h cross has the dimension of frequency. See, this term is actually like we can write this as e raised to minus I omega t, where omega is the frequency of oscillation, and this e raised to minus I omega t is cos omega t plus I minus I sin omega t. So oscillatory part is all there. So what is this angular frequency omega? ei minus ef by h cross. Okay. So the frequency of the oscillating electric dipole in the hydrogen atom is ei minus ef by h cross. What is this ei and ef? See, this is it. Ei is the energy of the initial state from this figure. Ei is the energy of the initial state, ef is the energy of the final state. So when during a transition there will be an oscillating dipole moment for the hydrogen atom, and the frequency of oscillation is ei minus ef by h cross. So the electric dipole moment will be oscillating with the frequency ei minus ef by h cross, then it will emit electromagnetic radiation of the same frequency. So during a transition from an initial state of energy ei to a final state of energy ef, the frequency of the oscillating electric dipole moment is ei minus ef by h cross, and the frequency of the emitted radiation is ei minus ef by h cross, angular frequency. Okay. So this is again, remember, this is again one of the postulates in Bohr atom model, but here we are able to obtain this directly from basic theory. Okay, in quantum theory model of the hydrogen atom. Now let us see what is the idea of selection rules. So we know that the intensity of the emitted radiation during a radiative transition, the intensity of the emitted radiation is proportional to, we have seen the expression, it is proportional to p square, where p is the amplitude of the dipole moment, oscillating dipole moment. So the condition for a radiative transition to take place is that the dipole moment should be non-zero. Okay, the dipole moment should be oscillatory, and this oscillating dipole moment should be non-zero. There should be some oscillating dipole moment. That is a condition. So now we have established an expression for the oscillating dipole moment. Okay, the time dependent part of the dipole moment during the radiative transition. This is it. So this should be non-zero. We know the angular frequency of oscillation is ei minus ef by h cross, and for this to be non-zero, this integral has to be non-zero. Integral over all space, position vector r, phi f star, phi I, and this integral should be non-zero. So we can say that the general condition for a radiative transition is this integral r phi f star phi A, integration over all space. Okay, this integral should be non-zero. This is the condition for a radiative transition in an atom. Okay. Now the transitions for which this integral is non-zero, such transitions are allowed transitions. Okay, and if this integral is zero for different pairs of transitions, if this integral is zero, then that means that there is no time dependent part for that the dipole moment. So such transitions will not result in any radiation. So these are forbidden transitions. Okay, now suppose the full set of quantum numbers for the initial state are n, l and ml principal quantum number, orbital quantum number, and magnetic orbital quantum numbers of the initial state. And the full set for the final state are n prime, l prime, and ml prime. Okay. Then what is the condition for allowed transitions? That integral I can rewrite as integral over all space vector r. So that phi n star. So, okay, instead of phi what is that initial state? Phi f star, right? Final state. Okay, so that becomes phi n prime, l prime, ml prime. This is the final state, right? R phi. The initial state is n, l, ml. Okay, so this is the condition for a radiative transition in hydrogen atom, we can say. This integral should be non-zero. Now, if we consider different pairs of wave functions, hydrogen atom wave functions, and check this integral for whatever pairs this integral is non-zero, for whatever pairs it is zero, then for allowed transitions, we can get some conditions between principal quantum numbers, orbital quantum numbers, and magnetic orbital quantum numbers. And these conditions are here. This difference in principal quantum numbers can be any value. Okay, from any n value to any n value, transitions are allowed. But difference in L value should be plus or minus 1. Difference in ml value should be either 0 or plus or minus 1. Okay, so this we can get from conditions of considerations of parity of the states. We can deduce some results. But in general, in order to get all the results, we need to take into account different wave functions, and we need to do this integral and see which pairs of values are non-zero. So only these pairs of values are non-zero, so they can be deduced from symmetry requirements also, and these conditions are called selection rules. Selection rules for allowed transitions. So if these conditions are this first one we don't have to consider it, because delta n can be any value. So generally selection rules are between L value. Delta L is plus or minus 1. Delta ml is 0 or plus or minus 1 for atomic different transitions between radiative transitions between different atomic states. So those transitions which satisfy these selection rules are allowed transitions, and those transitions which do not satisfy these selection rules, they are forbidden. Okay. And one more point is that when you look at this integral, see the expression for dipole moment, the time dependent part of the dipole moment, it involves this integral, right? Now the magnitude, so if this integral is 0, it is forbidden. That means that there is no the time dependent part of the dipole moment is 0. That means that the dipole moment is, even if dipole moment is there, it is not oscillator, so there is no radiation emitted. If this is non-zero, there is some radiation emitted. We know the frequency of radiation is Ei minus Ef by h cross, and the condition for this integral to be non-zero are selection rules between L values and ml values. But what is the magnitude of this integral? The magnitude, if the magnitude of this integral is large, then actually this integral represents the probability of transitions between an initial state and a final state. Okay, so if the magnitude is large, it means that the probability of transition is more. Then such spectral lines produced by such transitions will be more intense. If the magnitude of this integral is less, it is non-zero, but suppose the magnitude is less, then the probability of transition is less, so the intensity of such spectral lines will be less. Okay, so you can calculate the probability of transitions from the magnitude of this integral. This integral represents the probability of a transition from an initial state to final state. So we can calculate probability of transition, and this probability of transition decides the intensity of spectral lines also. So we have considered radiative transitions in hydrogen atom, and we have seen the condition for radiative transition, and deduced at least we have seen how we can deduce selection rules. Okay. Now let us briefly consider this idea of metastable states. See, okay, we have seen that for radiative transitions to be possible, this integral should be non-zero. Okay. but this integral is connected to electric dipole moment, right? So we have considered that the radiative transitions are due to electric dipole oscillations. So if this integral is non-zero, then we have an oscillating dipole, electric dipole moment, and we have a transition, radiative transition. Okay, but suppose this integral is zero, then there is no transition due to the oscillation of electric dipole. But even though even in the case of such forbidden transitions, so when we say that forbidden transitions, these are forbidden by electric dipole oscillations. Okay, electric dipole oscillations are not happening. But even in such cases, in some of these cases, not in all cases, transitions are possible by other processes. That means radiative transitions are possible by other processes. So far, by radiative transitions, we have considered only dipole oscillations, oscillations of electric dipole. Now, if oscillations of electric dipole are forbidden, there is no time-dependent part for the for the electric dipole moment. What are the other processes by which radiative transitions are possible? One such process is oscillations of magnetic dipole. Oscillations of magnetic dipole. In an atom. Okay. That means we know that current loop can act as a magnetic dipole. So in atoms there is this possibility that this current loop, current loop, its orientation is reversed continuously. So that means this current loop is oscillating. That means when the current loop is in one orientation, the dipole is in one direction. When the direction of the current loop, current loop is its orientation is reversed, then the direction of the dipole moment will be reversed. So in this type of here it is magnetic dipole moment. Okay, a current loop represents a magnetic dipole moment. So when this current loop switches or swaps orientations, the magnetic dipole moment will be oscillatory, and this oscillations of magnetic dipole moment will result in a radiation. But this is a less efficient radiation compared to oscillations of electric dipole. So it's a slow process. Okay, the emission of radiation by radiative transitions by the oscillations of magnetic dipole is a slow process, and it's slower than the oscillations of electric dipole by a factor of 10 raised to minus 4. Okay, it's slower by a factor of 10 raised to minus 4 compared to oscillations of electric dipole because it's less efficient. Now another process is oscillations of electric quadrupole moment. Quadrupole moment. Okay, I am not going to define what is an electric quadrupole moment. So this oscillation of electric quadrupole moment, oscillations of electric quadrupole moment, or also can result in radiative transitions, but this is again even less efficient compared to even oscillations of magnetic dipole. So this is even less efficient, and hence it is even slower. Okay. So these are two processes by which radiative transitions can occur other than oscillations of electric dipole. Oscillations of magnetic dipole and oscillations of electric quadrupole moment. So understand that each of these processes are progressively less efficient, and hence it's more slow compared to oscillations of electric dipole. Normally in the case of atomic excited states, the major radiative transition, major process of radiative transitions is, as we have seen, oscillations of electric dipole moment. And for those atomic excited states in which the radiative transitions are due to oscillations of electric dipole moment, their lifetime, average lifetime is of the order of 10 raised to minus 8 seconds. Okay. But there are some states, some atomic excited states where these oscillations of electric dipole moment do not happen. They are forbidden. but this oscillations of magnetic dipole moment or oscillations of electric quadrupole moment can happen. Okay, but since these are less efficient process and such radiative transitions from an initial excited state to a final state, such radiative transitions will be slow. So if the radiative transition is slow, then this excited state will be having a longer, significantly longer lifetime, very much longer compared to 10 raised to minus 8 seconds. Now such states are called metastable states. So metastable states are atomic excited states having lifetime significantly longer than this 10 raised to minus 8 second. The reason is that in such metastable states, the radiative transition is not due to the oscillations of electric dipole moment, but one of these processes, maybe both, oscillations of magnetic dipole moment or oscillations of electric quadrupole moment. Okay, magnetic dipole moment. Yeah. So these metastable states are longer lived, and they have a key role, and they are very important in the production of lasers. Okay, laser action happens between so the existence of metastable states are necessary for laser action. Okay, so you will learn more about metastable states when you study laser. So understand that the mechanism behind the longer lifetime of metastable states is this. In such states, radiative transitions by oscillations of electric dipole moment are forbidden. But other processes like oscillations of magnetic dipole moment, oscillations of electric quadrupole moment are possible, but they are less efficient and hence slow. That is why these states are longer lived. Okay, so this is our discussion. This concludes our discussion on radiative transitions. So we have seen in this class, we have seen that what is the idea of this dipole oscillations, right? We have taken this idea from classical electrodynamics, the idea of dipole oscillations and radiations emitted by electric dipole. Then we have also seen that when the electron is in a particular quantum state, such states are stationary states, non-radiating states, because probability density is time independent and the expectation value of position vector of the electron is time independent. If the expectation value of position vector is time independent, dipole moment is time independent, so there is no radiation. Okay, these are stationary states. Then there is this spontaneous decay due to vacuum fluctuations, and during such spontaneous decay, what is the frequency of electric dipole oscillations? We have seen that the frequency is exactly EI minus EF by H cross, right? And what are selection rules? Selection rules are obtained. See, the time dependent part of the oscillating dipole moment is this, and it involves an integral, this type of an integral. So only if this integral is non-zero, we have an allowed transition. If this integral is zero, the transition is forbidden, as far as electric dipole oscillations are concerned. Okay, so the condition for this integral, so that's a condition for allowed transition. This integral should be non-zero, and when you work out pairwise for the hydrogen atom wave functions, or for generally for any atom, this is the conditions. Delta L is plus or minus 1, delta ML is 0 or plus or minus 1. These are called selection rules. And then we have seen that even though radiative transitions are forbidden by electric dipole oscillations, other processes are involved which are less efficient and slow, which leads to longer lifetime for excited states, and these are called metastable states. Okay.